In this video, we're going to talk about some advanced properties of standard Brownian motion. The first property is known as self-similarity. And this is really neat. I think this is my favorite property. So suppose that z of t is standard Brownian motion, and we're going to define a new process, u of t, to equal c times z of t over c squared for some constant c greater than 0. So essentially we're taking our process and looking at it in sharper detail, looking at it more closely in the time interval, and then scaling up that process by a factor of c. Well, because this is a transformation of a normal random variable, it's still going to be normal. We could find the mean of u of t. It's going to be taking that constant outside, just c times the mean of the z process, which is 0. So c times 0 is 0. And the variance of u of t will be the variance of c times z of t over c squared. When we pull the constant outside, we square it, and then that's going to give us an overall variance of t. So what we've shown is that u of t is normal with mean 0 and variance t. And as well, u of 0 will equal 0, and we'll sort of inherit those properties of stationary and independent increments. So if you remember the definition, u of t is itself standard Brownian motion. This is so cool. This means kind of if you zoom in on a Brownian motion process, what you get when you look closer is another Brownian motion process. It's like a fractal. If you've ever seen those cool videos, I'll maybe see if I can post some of zooming in on a fractal, and it just looks the same as it did before. It's kind of cool. So let's see if we can try this. I'm going to try and help you visualize this. Imagine that we take a standard Brownian motion process and zoom in on it on a sample path. So I'm going to zoom out here to start, draw my standard Brownian motion here. There's t, there's z of t, and there's our Brownian motion process. It starts at 0 and it goes all over the place. If we zoom in on part of it, it still looks just as jagged as before. And if we zoom in on that, it still looks just as jagged as before. So if we zoom in as close as we can, this is as close as my program can get, it doesn't look like a smooth curve. If we zoom in closer and closer and closer, it's still going to be that super jaggedy line. So let's go back to a normal size view here. No matter what, it keeps looking as jagged as ever, no matter how closely we look at it. You can zoom in infinitely far and it will still look the same, which means if we tried to, we could never take a tangent line of this process, which leads to it being nowhere differentiable. Isn't that neat? So cool. So essentially the sample paths of this standard Brownian motion process, and by extension the other types of Brownian motion, have the properties of fractals. All right, the next property is talking about the joint distributions of the values at 2 points in this process. If we wanted the joint distribution of, say, z of t and z of s, where s is greater than t and both are greater than 0, we could define the following. Let's let x equal z of t, we know that's normal 0t, and y is going to be the increment, z of s minus z of t, and we know from the previous video that this is normal with mean 0 and variance equal to the difference in the times, so s minus t. And we know, of course, because this process has independent increments, that x and y are independent random variables, and hence the sum of them, which would be just z of s, is going to be normal with mean 0 and variance s. As well, since both of those random variables are normal, their joint distribution is going to be multivariate normal, if we remember that from chapter 2. So for a multivariate normal, we need a mean vector, mu, which is the mean of each of those variables, but both of those are just equal to 0, so this is just a 0 vector. And we also need our variance-covariance matrix, which we call capital sigma. It's defined as, the variance of one of them and then the covariance of the two of them, as well as covariance down there and the variance of the last one there. And we know that the variance of z of t and the variance of z of s are t and s respectively. But what about those covariances? Let's take a little aside over here. The covariance of z of t and z of s, we could write that as the covariance of x and x plus y, the way we've defined them here for a little shortcut. Well, the covariance of x with x plus y is the covariance of x with x plus the covariance of x with y. But the covariance of x with x is just the variance of x, and x and y here were independent, the way we defined them, because they were covering non-overlapping periods in this process. So altogether, the covariance of z of t and z of s is just the variance of x, which was our normal 0t, and so the variance is just t. So both of those diagonals of that matrix will be t. So altogether, we could say that the joint distribution of z of t and z of s is multivariate normal with this mean vector 0, 0 and variance covariance matrix t, 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 s. we could actually generalize this further and get the joint distribution of any number of random variables that we like. We could take as many z of ti's as we want, and the resulting joint distribution will be multivariate normal, with the mean vector just a zero vector, and the variance-covariance matrix as follows. All the diagonals will just be ti, and the off-diagonals, the covariances, will just be the minimum of the 2 times ti and tj. So that's pretty neat. We can get the joint distribution of any number of values of this process, as many as we like. For the third property, I want to think about the conditional distributions for this process. Suppose we have s greater than t greater than 0, 2 points in this process, and we could be interested in conditioning in one of 2 directions. First, we could think about looking at z of s given z of t is equal to a. So that's kind of conditioning forwards in time. We know where we are at time t, what's going to happen later after that point. Or we could condition in the opposite direction, z of t given z of s equals b. So that's kind of conditioning backwards. So we know where we got to by time s, but what does that tell us about where we were at time t at an earlier point in the process? See if you can think logically about what these distributions might look like, conditioning forwards in time or conditioning backwards in time. Well, the first one is pretty easy. For a, we already know that the distribution of the increment, z of s minus z of t, is going to be normal with mean 0 and variance s minus t. And so we could just write z of s as z of t plus that increment. And then if we're conditioning on z of t equaling a, then that value is fixed. So then z of s, given this condition, is just going to be a plus this normally distributed amount with mean 0 and variance s minus t. So altogether, that's going to have a distribution with mean a and variance s minus t. Let's see what that looks like. If we draw out a Brownian motion here, we'll have t there, z of t. There's our jaggedy Brownian motion, there's time t, and at that point the process has a value of a. So again, we can imagine the process sort of starts all over again at that point, and then the distribution at time s is going to be normal with the mean equal to where we were at time t. If we know where we were, we can imagine the process starts again from that point forwards. And again, the variance is just the difference in that time interval, s minus t. For b, though, conditioning in the opposite direction, it is a little bit trickier. I'm not actually going to show the proof in this video, but I might make a bonus video with the proof. It's just the coolest proof I've ever seen. But essentially, we use a joint transformation, and we can show that this conditional distribution is normal with mean equal to b times t over s, and variance t times s minus t over s. I want you to think about why that makes logical sense, why the mean and variance are what they are from this result. Well, let's see if we can draw it out to help visualize it. If we have Brownian motion here, again, drawing my axes and drawing my jaggedy path of my Brownian motion, we're saying we know what happens at time s. We've reached a value of b. And we're wondering what happens at time t, which is some point before time s. Well, we know that the process was at 0 at time 0, and it gets to b at time s. And in between, on average, it's going to follow a straight line. It's not necessarily going to be exactly that straight line, of course. There's randomness around it. But on average, if we know where it was at those 2 points, at the start and end of this time period, then in between, it follows a linear relationship. So if t is really close to 0 or really close to s, we're pretty sure we know what's going to happen. We would expect z of t to be really close to 0 or really close to b, z of s, with a pretty small variance, because if we know where we are a second later, it can only go so far in between. But if t is somewhere in between, in the center, then z of t will be on average somewhere between 0 and b. And it'll be linearly related. It'll be proportional to the distance along that time interval that it's traveled, a linear function of t. And the variance, of course, is going to be the largest when t is right in the middle between 0 and s, and it'll get smaller when it gets closer to those endpoints. So hopefully that makes some logical sense why z of t is going to have a mean of b times t over s and a variance of t times s minus t over s. So the mean is proportional to how far along that time interval we've gone, and of course proportional to b. And the variance is going to be a function that's highest in the middle, so this is maximized when t is half of s, and smaller at those endpoints, close to 0 and close to s. Again, I will prove this in a separate video if you like, but this is a good logical explanation. All right, next property is about the first passage times of this process. So we're going to define t to be the first time at which z of t equals a value of a. In other words, it's the time it takes for the process to get up to the value of a for the first time. And it's pretty tricky to find the probability distribution of t directly, so what we're going to do is use a conditioning argument, looking back at chapter 3. So for now, we'll consider a positive value of a, and we want the probability that z of t is greater than or equal to a. Well, using conditioning, we can write this as the probability that z of t is greater than a conditional on t being less than or equal to little t times that same probability plus the probability z of t is greater than or equal to a given capital T is bigger than little t times that same probability. All we're doing here is just using the law of total probability or the partition rule, using a partition of capital T is greater than or less than little t. So a couple of things to notice here. First of all, if we look at the probability of z of t being greater than or equal to a, given t is greater than little t, that is going to be 0. And it's 0 because we've defined capital T to be the first time we get to the value of a. So if little t is less than big T, which is what we have here, we have big T greater than little t, which is the same as little t less than big T, then z of t cannot possibly have gotten up to a value of a yet, because if it had, then capital T would be not defined properly anymore. So again, think about that just for a second. It takes a little bit to wrap your head around it. Capital T, by definition, is the first time we get to A. So we can't possibly be at A or bigger than it before that time. So this conditional probability must be equal to 0. The other thing you want to look at is the probability that z of t is greater than or equal to A, given capital T is less than or equal to little t. And that we could just write as, using the increments, the probability that z of little t minus z of big T is greater than or equal to 0. And that's just equal to 1/2. So we can do that because we already got to the value of a at time capital T, and time little t is after that. So the additional movement that happens between time big T to time little t is going to be normally distributed with mean 0 and variance little t minus big T. And because it's normal with mean 0, the probability that it's positive is just 1/2. Again, a little bit of thinking that has to go into this argument. We've already gotten to A, so at any future time, the probability of being above or below A, this is standard Brownian motion, it's symmetric, so the probability is just 1/2. So taking our original expression there and piling all this new information in, we get that the probability z of t is greater than or equal to A is 1/2 times the probability t is less than or equal to little t, plus 0 times the probability big T is greater than little t. This first quantity here is just 1 minus the CDF of a normal 0t evaluated at the value of a. That second term disappears, and that there, the probability that t is less than or equal to little t, by definition, that is the CDF of the random variable t that we're looking for. So piling this all together and solving, we can get that the CDF, big F sub t of little t, is 2 times the probability that z of t is greater than or equal to a, which is 2 times 1 minus the standard normal CDF evaluated at a over root t. This was all assuming that a was positive, but if a is negative, we end up getting a very, very similar result. We just end up with the absolute value signs on the a. So we'll add those in, bloop, bloop, and that gives us the expression. If you wanted the probability density function of t, you could take the derivative of big F of t with respect to t, and you would need to use the chain rule. It would be a bit of a mess, but you could do it. You could find the derivative with respect to t. Just be careful. I also want you to think about why this expression makes sense. So if the absolute value of a is larger, in other words, we want to get farther away from our initial value of 0, then this function, big F sub t of t, is going to be getting smaller. You can see it's a decreasing function of the absolute value of a. And what that tells us is that on average, it's going to take longer to get there because the probability of the time being less than or equal to little t is smaller, which means it's going to take longer on average. And that should make sense, right? The farther away from 0 we want to get, on average, it will take longer for that to happen. All right, the last property is the distribution of the maximum. So often we might be interested in the highest value or the highest point of this process within a particular time interval. And a common application of that would be the maximum price of a stock within a certain time period. So we can let W of t equal the maximum of Z of R, where R is between 0 and t, and that's just the maximum in the interval from 0 to t that's attained by this standard Brownian motion process. One thing that's interesting is that W of t, this maximum, is always going to be positive because of self-similarity. Essentially, if you just keep zooming in on the process at Z of 0, eventually it will go positive, even for maybe a tiny second of time. And that's kind of weird to think about, but just, even if it looks like it starts going downwards, just zoom in closer. And if it still looks like it's going straight down, zoom in closer. Eventually, you have infinite many zooms that you want. Eventually, it will go positive for a tiny little bit. So the maximum that it attains on any time interval is strictly positive. So then to find this distribution, I want to recognize that the event that W of t is greater than or equal to some value little w is exactly equivalent to the event that the first time to reach a value of w is less than or equal to little t. See if you can convince yourself of this fact. If the maximum value is at least w by time t, that means that the time it took to reach w must be less than or equal to t. Those two events are exactly equivalent, and again, little w is positive here. So because those two events are equivalent, the probabilities of them are equivalent. So the probability that w of t is greater than or equal to little w, that's the probability that t, the time to reach w, is less than or equal to little t. Well, subbing in the result that we got from property number 4, that gives us this, and thus the CDF of w is 1 minus that result there. Similarly to before, if we wanted, we could find the PDF of w by taking the derivative here with respect to w. Again, we would need the chain rule. It would be a bit of a mess, but you could do it, and that would get you all the information you want about the maximum value in this process within a given time interval. All right, let's take all of these properties and put them into practice with one big example. Suppose we have a standard Brownian motion process, Z of t, where t is greater than 0, and I want to find 4 things. First of all, the probability that Z of 3 is greater than or equal to 4, given Z of 2 is equal to 3. Second of all, the exact opposite, Z of 2 is greater than or equal to 3, given Z of 3 is equal to 4. The first time to reach 4 happening between time 2 and time 3. And finally, that the maximum by time 3 is less than or equal to 4. Again, I want you to give these 4 properties a try to calculate them yourself using these advanced properties, and then come back and watch the solutions. All right, here we go. So we know from property, 3a, that the distribution of Z of 3 given Z of 2 equals 3 is normal with mean 3 and variance 1. The 3 comes from the fact that Z of 2 was equal to 3, and the 1 comes from the fact that time 3 is 1 time unit later than time 2. So we have this normal 3, 1. And thus the probability that that random variable is greater than or equal to 4 will standardize, subtract the mean, and divide by the standard deviation. So 4 minus 3 over the square root of 1, that gets us a probability of 0.16. For B, we can use the property 3b, to look at the distribution of Z of 2 given Z of 3 equals 4. Well, that's going to be normal with mean 4 times 2/3, because b is 4 here, and we're looking at what happens 2/3 of the way along this interval. And the variance is just 2 times 3 minus 2 all over 3. So that's a normal with parameters 8 over 3 and 2 over 3. And we're looking for the probability that this random variable is greater than or equal to 3. So again, standardizing, we'll subtract the mean and divide by the standard deviation. So 3 minus 8 over 3 over the square root of 2/3. And that gives us a probability of approximately 0.65. For C, we can define t to be the time it takes for the process to reach a value of 4 for the first time, and we want t to be between 2 and 3, which is just the probability it's less than or equal to 3 minus the probability it's less than or equal to 2. While subbing in what we know for the CDF of this random variable t, we can get this expression here, and if you evaluate that, it should be about 0.016. And then finally for D, we're looking for the probability that the maximum by time 3 is a value that's less than or equal to 4. So again, subbing in this expression here and evaluating, we get a probability of 0.979. This was all using standard Brownian motion, but any of these questions could be asked using Brownian motion with drift or even geometric Brownian motion. And the key is always to just convert any problem into a statement involving standard Brownian motion. So either by taking the log of both sides or subtracting mu t on both sides or whatever you need to do to turn it into a statement about z of t, this process, and then use these advanced properties. So there are some really neat advanced properties of the standard Brownian motion process, which can then be used to tell us interesting stuff about other Brownian motion processes. We have the fact that it's self-similar, we have the joint distribution and the conditional distributions, either forwards or backwards in time. We have the first passage time, as well as the distribution of the maximum. And all of those things, again, you can do for standard Brownian motion, or using logarithms, do it for geometric Brownian motion as well. So that brings us to the end of Chapter 6, and actually the end of the material for the whole course. I will see you in the next tutorial on Wednesday, where we'll do an activity to wrap up the whole course. See you then!